This chapter is called Thermionic Emission and Radioactivity. We have already covered thermionic emission as in the cathode ray tube, and now we get into radioactivity. But to understand that, we have to know the atomic structure. A lot of scientists contributed in developing the modern theory of the atoms, but it started with Dalton talking of atom. Atom means something that cannot be cut or something that cannot be further divided. That's why we call the atom the atom. But his model was rejected because Thomson came up with an experiment that proved that Dalton's model cannot be correct. So Thomson's model was plum pudding. But then Rutherford came in later and did his scattering experiment, which proved that Thomson's model is also not correct. Because Rutherford's scattering model did not explain the stability of the atom. So today, for 10th standard, we are going to stick with Bohr's model, but for your information, even Bohr's model is not correct. The correct model of the atom is actually quantum mechanical. Welcome to the portals of real learning. Don't skip and listen carefully right till the end. Let's now understand the atom. We briefly talked about it, right? That electrons are going around the nucleus and the nucleus contains protons and neutrons. That electron is negatively charged, proton is positively charged. How did we arrive at all this, first of all? The nature of matter was a mystery for a very long time. The mystery was people did see difference between materials in terms of their physical and chemical characteristics. Consider, for example, iron versus copper versus aluminium. They look different, their hardness is different, the chemical reactions are different. So the thought was, suppose you break down the iron piece and the copper and the aluminium pieces to as small particles as possible. We can't break it down any further. Even then, each particle, though it looks similar in size, is essentially different. There must be something within the particle that makes it different physically and chemically. So Dalton developed his atomic theory and he called it atom. Atom, by the way, is atom. A means cannot be done or not, and tom means to cut it or break it. So atom or atom is something that can't be broken or cut. And he said that all matter is made of indivisible particles called atoms. All matter is built of atoms. And they cannot be created or destroyed, and he imagined them to be tiny, hard spheres. Obviously, elements are different, so atoms of the same element have identical mass and physical properties, and they are different from the atoms of another element. It should be, otherwise, what is the reason for the difference in physical and chemical properties? He also said that the compounds, that is, combination of two elements like sodium and chlorine gives you sodium chloride, common salt. They are combinations of atoms of two or more elements, and all chemical reactions, they involve the rearrangement of atoms in some way. Actually, now we know that chemical reactions involve electrons. They don't involve the nucleus. J.J. Thomson, when he discovered the electron in 1897, after the work done by Thomas Alva Edison on thermic emission, he found that negatively charged particles are getting emitted and they could be deflected by this electric field between the positive and negative plates. And he also saw that the same kind of particle is emitted no matter what is the choice of the filament. In other words, you may choose an iron filament or a copper filament, both of them are emitting electrons. That means the atoms of these elements are containing electrons. The question is, what is the reason for their differences? That means something else needs to be studied. Okay, they have electrons, but what is the reason for the physical and chemical properties? And also, electrons were negatively charged, but atom as a whole was not charged. It was neutral, so there must be some positive charge inside it. Where is that sitting? I must tell you that J.J. Thomson actually measured the charge to mass ratio. He couldn't measure the charge, he couldn't measure the mass, but he could measure the charge to mass ratio. It was later that Millikan came in and measured the charge on an electron, and coupled with J.J. Thomson's measurement of charge to mass ratio and Millikan's experiment that told us the charge on the electron, we could calculate the mass of the electron. Let's talk about Thomson's experiment. We have thermionic emission, and electrons are coming out, and those electrons are accelerated by this voltage. They are also focused, they come with some speed v. This electron beam is now passed through a region where there are crossed electric and magnetic fields. Electric and magnetic fields are perpendicular to each other. And then we have a device, a detector, which will basically say, okay, I have received one electron here. Now, the kinetic energy of the electron, because of the speeding up, is half mv squared. But that is equal to the potential energy gained thanks to the accelerating voltage. We have talked about it. So if you accelerate an electron through a potential difference of v volts, then it acquires a kinetic energy equal to EV. And that is why electron volt is a unit of energy. So we equate half mv square is equal to EV. From there we get V is equal to root 2E capital V divided by M. This is the speed and this is the accelerating voltage. And we found that if we adjust the values of E and B in such a manner that E by B is equal to V, then the electron doesn't get deviated and hits the detector. This is something that you learn in 12th standard about this ratio of E and B. So if you equate V is equal to E by B equal to the previous expression, then we are able to calculate this ratio, charge to mass ratio, and that turns out. We know the E, we know the B, and we know the accelerating voltage. He was able to calculate the charge to mass ratio of the electron. Now, Dalton talked about his theory of indivisible particles. Thomson's experiment negated that atoms are not indivisible. There are subatomic particles like the electron. So he came up with a model which explained the neutrality of the atom, that the atom doesn't contain any net charge. And he said that there is positively charged matter which is like the pudding, and the electrons are negatively charged particles. They are sitting like the plum pudding model. And he theorized that the total charge on that positively charged matter is equal to the total charge on all the electrons, and therefore neutrality is explained. And he could also explain thermionic emission, saying that look, the electrons are attracted to the base, the positively charged base, and in order to eject it, we need to supply some energy. So he could explain thermionic emission and therefore ionization. When electrons leave, they leave behind a positively charged ion. But it was not accepted completely because of the first question of stability. What is the reason for electrons to be sitting around there in a stable manner? Of course, they are attracted to the positively charged base, but they are repelling each other. So who decides where they should be placed, and how is it that we can guarantee that this is a stable environment? The other thing also was later on we saw an experiment by Rutherford, which was penetration through a gold foil, and that therefore meant that even Thomson's model has to be rejected. So Dalton's theory was rejected. Later on, Thomson's model improved upon Dalton's theory, but that was also rejected. And Rutherford came up with another model of the atom. And what he did was he took a thin gold foil over here, very, very thin. And then he had a source of some alpha particles. And alpha particles are basically two protons and two neutrons together, which is actually the nucleus of the helium. He took that source, accelerated those alpha particles, and bombarded this gold foil. It was found that most of the alpha particles penetrated through the gold foil and went totally undeflected. Most particles are undeflected. Majority of them are undeflected. Some of them are scattered a little bit, and even fewer of them are returned with an angle of almost 180 degrees. But the fact that most particles went undeflected, that means that gold atom that is there is containing a lot of empty space. Contains nothing. It's all empty space. That is why the positively charged particles are able to penetrate through it and go undeflected. Now, the fact that a very small number turned by 180 degrees, it meant that there is a very small part of the atom that is strongly positively charged, and when alpha particle is coming, there is a small part within the atom which is highly positively charged, which repels the alpha particle by 180 degrees. But it was a very small part of the atom, and how did we conclude that? Based on the numbers. The number of alpha particles that returned by 180 degrees was a very tiny number. And this small part was called the nucleus. And this nucleus was a positively charged region. So we are arriving at a model where there are electrons and there is a nucleus which is positively charged. And clearly, the amount of charge on the nucleus should be equal to the total negative charge on the electrons. The electrons themselves could not be within the nucleus because then they would be held in a very tight attraction by the positively charged nucleus. It would be very hard for us to eject an electron, but we know it is quite easy to eject an electron. So if electrons are not part of the nucleus, they must be moving around it. They have to move. If you're not inside the nucleus and you're outside, then the attraction by the nucleus is going to pull it towards the nucleus and they will collide and electrons will go inside. But electrons are not inside the nucleus, they're outside. They have to move. Just like the moon is moving and therefore it is not coming and colliding with the earth. So the thing is electrons around the nucleus. If electrons must be moving around the nucleus, it must be in a closed loop like this, possibly the yellow one or the white one. White one is circular, yellow one is elliptical, or some other random blue type closed loop. If it is moving around, then it can't be leaving the nucleus completely. It has to move, but it has to move in some region, and therefore it is a bounded system, we call it. Electrons are bounded to the nucleus. But if you are going in a closed loop, then your velocity is changing, isn't it? Direction of the velocity is changing, which means you are accelerating. Now, there was a scientist called Maxwell who had developed his four laws, and by Maxwell laws, he said that any charge, if it accelerates, it must radiate electromagnetic waves like light or heat or something else. If it is accelerating, it must emit electromagnetic waves, which is energy. And if something is emitting energy, then it must be losing energy. So if electrons are accelerating, they should send out electromagnetic waves and in the process lose their energy and therefore spiral down to the nucleus. That doesn't happen. So because of Maxwell laws, we have to reject Rutherford's model also. This is unstable. Electrons can't be going around like this as per Maxwell's law. It is an unstable thing. Thomson's model was unstable. Rutherford's model is also unstable. So this was all improvement, right? That is how we build our knowledge. Then came another scientist called Niels Bohr. and he developed a model, and he said that the nucleus indeed is small and positively charged, and electrons go around it in a circular orbit, and there are many possible orbits. The maximum number of electrons in any orbit is 2n square. Number was given. The closest one is n equal to 1. This is n equal to 1. The next is n equal to 2. The next is n equal to 3. So the maximum number of electrons that can be accommodated within one orbit is 2n square, where n is the orbit number or shell number in the nth shell. If you take the first orbit, n is 1, so 2 into 1 is 2. The smallest orbit can take 2 electrons. The next orbit, n is equal to 2. So 2 into 2 square is 8. So the second orbit can hold maximum 8 electrons. The third one, n is equal to 3. 2 into 3 square, 18. Maximum number. So when you have various elements, what they differ by is by the number of electrons within the atom. That is what decides its chemical properties. And therefore, they're arranged in a certain manner called the periodic table. So what is the reason for the difference? Number of electrons. So suppose I have 11 electrons, like sodium atom. How will they go and fill up the orbits? They start filling from the smallest orbit. So 2, and the second one will have 8, 8 plus 2, 10, and the last remaining one will be in the third orbit. There's a principle that electrons start occupying their seats based on lowest energy first. Imagine it to be like an auditorium, lots of seats, and electrons have to go and take their seats. They will start taking those seats which correspond to the smallest energy level and then fill up everything accordingly. So the smallest orbit has the least energy, and as you go away from it, then it has got the maximum energy. I'm talking of the total mechanical energy, which is a sum of kinetic and potential. But then, even Bohr's model is talking of circular orbits. Is it not violating Maxwell's law? If you go in a circle, you're accelerating. And Maxwell's law says if you're accelerating, you have to emit energy, you have to emit electromagnetic waves. So therefore, you lose energy and they will go and crash into the nucleus. So how is Bohr's model justifying this? Bohr said that I don't know the real reason, but these orbits are what is called stationary orbits. Each orbit has got a distinct energy level, and as long as an electron is within that orbit, then it does not emit anything. Hence it is stable. He didn't have any solid reasoning behind this, but that is what he postulated, Niels Bohr. So let us understand Bohr's model. I must say that it is an approximate model, a very approximate model, but at least it explains a few things, and it is an improvement over Rutherford's model. So I've drawn here the red nucleus and various orbits, and I'm showing just one electron, the blue one, that is going around in orbits. Bohr said that all electrons move around the nucleus in circular orbits, and these orbits are stationary. Stationary means no electromagnetic wave is generated and there's no loss of energy. Now, as we just discussed, electrons in higher orbits have more energy. So if an electron were to jump from n equal to 1 to n equal to 2, that means it is acquiring energy from some source. If you make the electron absorb energy, then it will have to jump to a higher orbit. We say it has gone into an excited state. N equal to 1, if the electron is in the smallest orbit, then we say that the whole atom is in the ground state. And if n is greater than 1, then we say that it has gone into an excited state. N equal to 2, n equal to 3, n equal to 4, they are all excited states. N equal to 2 will have more energy than n equal to 1. N equal to 3 will have more energy than n equal to 2, and so forth. Now look at this animation. This blue electron is going in n equal to 1. Okay. So when I tell you, please look at it. Ready? 1, 2, 3. Once again. Ready? 1, 2, 3. Once again. Ready? 1, 2, 3. At that time, something was coming in. The electron absorbed it and jumped to n equal to 2. And that something is energy. A packet of energy. And that packet of energy is called a photon. Photon. So when it goes to n equal to 2, then it is in an excited state, more energy. And anything that has more energy will try to come to stability by releasing excess energy. So from 2 to 1, it de-excites. And when it de-excites, it releases an amount of energy represented by the arrow that is going away. So again, take a look at it. Ready? Ready? 1, 2, 3. Once again, ready? 1, 2, 3. It has jumped from 2 to 1 and emitted a photon, which is a packet of energy, and that constitutes an EM wave also. An EM wave is a wave, sure, but there's a theory, and very well established theory, that they actually consist of packets of energy, photons. So Bohr's model has its limitations, but it is a good start. Let's talk of the limitations. Why orbits must be stationary is not explained. It was just postulated. Later on, another scientist, D. Broglie, came in with his theory of wave-particle duality, and then he could give a justification for Bohr's model. What is wave-particle duality? Light is a wave, but it also behaves like particle sometimes. Electron is a particle, but it behaves like a wave sometimes. So everything has got a dual nature. So EM wave is a wave, light is an EM wave, but it behaves like particles, and photon is that model which is talking about the behavior of light as a particle. The second limitation was, why should the orbit be circular? There was no justification for that. And also this model is fine, it works only for those atoms which have got a single electron, like hydrogen. Hydrogen atom has got one proton as a nucleus and one electron. That's it. So Bohr's model works only for those atoms which have got only one electron. If there are more than one electrons, then this model doesn't work. So hydrogen atom is one. Helium atom from which one electron has been knocked out by some other process. So what now remains is a helium ion which is singly ionized. Singly ionized means one electron has been taken out. So it is now left with only one electron. Helium has got two electrons. If you take out one, it becomes a singly ionized helium ion. So now it is a single electron atom, and Bohr's model can be applied. Similarly, lithium doubly ionized. Lithium has got three electrons, and if you take two out of them, then only one is remaining and the model works. Those are the limitations. So what is the correct model of atoms? The correct model is quantum mechanical in nature. That's a very, very interesting physics. Quantum mechanical model accepts that electrons can't be inside the nucleus. They move around the nucleus, but not in orbits, not in definite orbits, either circular or elliptical or whatever else, not in definite orbits, but in orbitals. And what are orbitals? They are a region in which the electron is most likely to be present. That is, the probability of finding the electron in a region is 90 to 95%. Probability, we can't be sure where the electron is. And the shape of the region can be spherical or dumbbell or others. There is a principle of uncertainty called Heisenberg's uncertainty principle, which says we can't precisely tell where the electron is and what is its momentum at this given instant. We can't tell both the things. What is the position and what is the momentum? We can't precisely tell both the quantities at a given instant. There is some uncertainty around it. The uncertainty in position and the uncertainty in momentum, if you multiply those two uncertainties, they should be greater than some particular value. These quantum mechanics concepts you are going to learn much later in life. Even in 12th standard, you'll learn just a little bit. You'll learn all of this more in professional colleges. I just want to tell you that Bohr's model is very inaccurate, but still useful for certain limited situations. So we'll stay with the Bohr's model and we will continue this discussion forward.